Okay, in this lecture, we're going to talk about the investigation, are all atoms equal? The quote that we have is, great minds discuss idea, average minds discuss events, and small minds discuss people, from Eleanor Roosevelt. And in this unit, what we're going to do in this investigation, we're going to talk about the idea of atomic trends and isotopes. What we're hoping to accomplish by the end of this lecture is, the first thing, students will be able to use ionic notation. We'll be able to use it, write it in its form. The second thing, students will understand the trends that govern electronegativity, ionization energy, and ionic radii. When we're looking at those things, we want to be able to look at a periodic table and know what's going to have a higher electronegativity, a lower electronegativity. Same thing with ionization energy, and same thing with atomic radii. And the last thing we want to be able to do, students will be able to calculate average atomic mass or percent abundance of an isotope. And we're going to discuss a lot about isotopes in this lecture. Now, an ion. Let's talk about what an ion actually is. The first thing, electrons can be added or removed to an atom. So they can an atom can either get an electron or lose an electron. In this case, if you look over here, we see that we have our nucleus in the middle, and then we see that we have our electrons. And we see that an electron has been removed here. And what this is going to do is this going to create an unbalance, meaning we're going to have, if we look here, we have 1, 2 protons, and now we only have 1 electron. So it's created an unbalance in the charge. Okay, now protons can never be removed in a chemical reaction. So when we have our protons in our nucleus, in a chemical reactions, this never changes. So we can't add any more positives. We can only work with the positives that we have. Now, anions have more electrons than protons. If we look here, we had 2 electrons, but if we took one away, we see that we have 2 protons and only 1 electron now. So that means that we have more. Okay, that's what we call a cation. A cation has more protons than electrons. So basically, we have a plus here and a plus here, and we have a negative right here. Well, a positive and negative, they'll balance each other out, but what we'll see is we'll be left with a single positive charge. And this positive charge, that's what the ion actually is. So if we have a positive charge, we have a cation, and you can kind of think of it, the cation has a T in it, so it's positive, and anions has an N in it, so it's negative. Okay, so cations are positive, anions are negative. Cations had an electron removed, and anions had an electron taken or given to it. Now, when we look at ion notation, what we need to do, and these are kind of the steps that we can follow to write our ion notation. Okay, we identify the number of protons. So we look at the number of protons in the nucleus. The second thing is we use the number of protons to identify the element. Third thing is we write the chemical symbol for the element. Number 4, we determine if the object is a cation, meaning it's deficient in electrons. We had electrons removed, so therefore it's going to be positive. Or anion, which has excess electrons, so it's going to be negative. And then we write the number of the surplus or deficit. Basically what we do is, if we're looking at this one right here, the atom that we see that we have 1, 2, 3, 4, 5, 6 protons. Okay, so when we look at it, if it has 6 protons, we look on the periodic table and we look at the atomic number and we see that it's a 6. And whatever has a 6, that's the element that it is. So a 6 would be carbon, so we just write C. Okay, now if we look, carbon has 6 protons, and let's see how many electrons we have. We have 1, 2, 3, 4. So we only have 4 electrons. So if we think about it, we have more protons than we do electrons. We actually have 2 more protons than we do electrons. Okay, so what we would get is we would write a 2 plus. So this would be carbon 2 plus, and this would be our ion notation. Now, When we talk about ions, it leads us into ionization energy. Ionization energy is the energy required to remove an electron, and it depends on the following: the number of positive charges, the number of negative charges, and the distance between the electrons and the nucleus. But this ionization energy, we can look at it and it follows a trend on the periodic table. When we look at it, ionization energy decreases as you move down the periodic table. So elements at the top of the periodic table up here will have a higher ionization energy than the elements on the bottom. So they decrease. So they go from the highest number to the lowest number. Now, ionization energy increases as you move across. So basically what we see is it increases, so the numbers over here are going to be low, and this is going to be high. The kind of general theme of this is that ionization energy increases in that direction. So helium will have the highest ionization energy of anything on the periodic table. Okay, and what we'll see is as it moves towards helium, it's going to have a higher ionization energy. Okay, and that's what we can look. We can look within a group, or we can look within a family, and we see that within a family, we'll see that the ones at the top will have a higher ionization energy than the ones on the bottom. Or if we look in a period, we see that the ones that are to the right are going to have more than the ones that are on the left. That's ionization energy. Now, the other trend that we see is electronegativity. And again, it has to deal with the elements and electrons. Now, electronegativity is a measure of an atom's ability to capture an electron, and it depends on the valence, those outer electrons, and their distance from the nucleus. So it has to deal with their valence electrons. The second thing is the number of protons that it has and the stability of the ion. Now, when we're looking at the trend of electronegativity on the periodic table, we see that electronegativity increases as you move up the periodic table. So the ones at the very bottom will have a lower electronegativity than the ones at the top. Now, electronegativity increases as you move across the periodic table. So it increases, and it basically, it's kind of like ionization energy. It follows the same trend. The exception to this is the trend excludes the noble gases. So when we look at the noble gases, they're going to be excluded from electronegativity unless under extreme circumstances where the question specifically states that something has happened to the electronegativity or happened to a noble gas, they might have electronegativity. But in general, everything is going to increase following the same trend of ionization energy, but instead of increasing toward helium, it increases towards fluorine. And it's going to give us that trend as we move across the periodic table. Now, one of the reasons why the noble gases aren't included is because you remember when we talked about the three things that electronegativity depends on, the third thing is stability of an ion. And basically what happens is the noble gases, they do not want to form ions. They don't. They never usually, under normal circumstances, ever form ions. And so they're never in chemical bonds. Okay, so they're excluded from electronegativity. I would also put here that electronegativity it's within a chemical bond. Okay, electronegativity, you gotta have it within a chemical bond, and that's in the context that we use it in. So it's gotta have that element bonded to something else. Now, ionic radii. Ionic radii can be determined by comparison with the size of the electron cloud it emulates. Basically what happens is you're looking at the electrons, you're looking at the valence electrons, and you're seeing how they look. Okay, so when we look at it, a lithium ion is nearly the same size as a helium atom. So basically what you're looking at when you're looking at your atomic radius and you're looking at that, ionic radii is basically the same thing, except if you look, a lithium ion had one electron removed, so how many electrons does it have? It has 1, 2. Okay, how many electrons does a normal helium atom have? 1, 2. So this lithium ion will have about the same size as helium because it has the same number of electrons. Now, example A1, it says, under what circumstances might a helium atom have a greater electronegativity than fluorine? So we're looking at the difference. Now remember, we said with electronegativity that we excluded the noble gases unless it was a crazy circumstance. And what we would have to actually do is we'd have to remove an electron from that helium, and we would make it a helium ion, which if you look at the ionization energy, remember that is the amount of energy required to remove an electron. Helium has the highest ionization energy, so it would be a crazy circumstance that we'd have to use a ton of energy to actually pull an electron away, and then we'd have to have helium in a chemical bond, which that is extremely unlikely, and you have to have some pretty different circumstances than just normal atmosphere, normal temperature, normal pressures, and all that stuff. So it'd be a crazy circumstance, but theoretically we could make it happen. Now, example A2, it says the attraction and repulsion between protons and electrons is responsible for atomic, ionic radius, ionization energy, and electronegativity. Explain how increasing the period of an electron decreases the ionization energy using the formula below. Okay, so we're increasing the period of electrons. The one thing that we have to understand is when we increase the period, we're increasing the energy level. We're increasing the distance. And so what we have to understand is we're going to use this equation below, and the one thing you should do when you're looking at this is look at the distance between the charges, the distance between the protons and the electrons. So if we increase the distance, what happens to the overall force? And then remember, you got to think, what is ionization energy? So those are some tips that we can use to try to work out this problem. Let's see if you can't get the right answer. Now, example A3. The answer that you should get here is you should get your beryllium with a 2+ charge for your ionic notation. Make sure you can tell me why. Now, we're looking at the nucleus, we're looking at electrons, we're looking how they're affected when we take and move electrons away, and we're leading into an extension of Thomson's experiment with neon that led to 2 different lines of neon. And basically what we would see here is that all the lines that are up here, those were known. Those were known to be contaminants, and they knew what they were. But what they saw with neon is they saw these 2 lines down here that are circled in that red circle. They knew what they were supposed to be. They knew that they were supposed to be neon, but they saw 2 different lines. And these lines could not be understood by our model of the atom, the Bohr model of the atom. And so basically what this led to is the discovery of isotopes. Now, isotope, basically what it is it's the same element, so it has the same number of protons, but it has different numbers of neutrons. Okay, so all versions of an element have the same number of protons, and we see that. Here's an example over here. We see that we have 1 and 2 protons and 1 and 2 protons. And so we see that it has 2 protons, and that gives it the ability to be neon, or to be helium, I'm sorry. So it's helium, and what we see is that the difference between the 2 is this has 2 neutrons and this has 1 neutron. They're going to have the same number of electrons and different numbers of neutrons. And the way that we distinguish between the 2 is we can write it in hyphen notation. You can see it down here written in hyphen notation. And all we do to write hyphen notation is we write what the element actually is. So we have helium. And then we have 4. And that 4 and that 3 that's right here, that represents the number of particles in the nucleus. So we have 2 protons and we have 2 neutrons. And that 3 represents the particles in the nucleus. We have 2 protons and 1 neutron. And so this mass number right here represents what's in the nucleus. And then helium, basically that tells us what it is. Now, another way we can write out what isotopes are is through nuclear symbol notation. And how we do this is the first step is we identify the number of protons to determine the element. Remember, that's how we always determine what element we have. It's by the number of protons. And then we write the chemical symbol for the element. And you can see that, again, we're using the example here. We have helium. And so we wrote the symbol for helium, and we see that it's here. The next step that we do is we write the atomic number on the bottom left corner of the chemical symbol. Remember, all the atomic number is just the number of protons. So in this case, helium had 2 protons, so the atomic number is 2. Okay? And then lastly, we write the mass number on the top left corner of the atomic symbol. So when we're looking at it, we know that in the one element, or the one atom of helium that we had 2 protons and 2 neutrons, so that's where we got the 4 from. And in the other atom of helium, we had 2 protons, because remember, 2 means that it's helium, and then 1 neutron, so this was helium-3. So this would be the nuclear symbol notation for helium-4, and this would be the nuclear symbol notation for helium-3. Now, with the isotopes and the different types of isotopes, the question that we have, if isotopes have different masses, what is the mass of hydrogen? Okay, we never specifically get, once we have hydrogen, what we actually have is we actually have a mixture of all the different isotopes of hydrogen. And what you'll see is that they'll have the atomic mass, which the atomic mass on the periodic table is actually not the atomic mass, that's the average atomic mass. The atomic mass, or in this case we can call it the mass number, that all refers to the mass of the nucleus. Okay, so what we're looking at is the number of our protons and our neutrons. So when we look here, this is hydrogen. In this hydrogen, what's in the nucleus is just the proton. So it's going to have an atomic mass of right around 1. Here, it's hydrogen because it has 1 proton, but it also has a neutron. So this would be hydrogen 2. And see here we have, again, 1 proton, in this case 2 neutrons, so that's going to be our hydrogen 3. And basically what we get is we get our atomic mass. Now our atomic mass is normally in what we call AMUs, atomic mass units. And it's just referring back to a system of measurement that's based off of carbon-12. Okay, but what we actually see on the periodic table is the average atomic mass. Now, to find this, the average atomic mass is an average of all the isotopes of that element. So in the case of this hydrogen 1, hydrogen 2, hydrogen 3, the atomic mass on the periodic table is a mass of all 3 of those isotopes. Now, to calculate the average atomic mass, it's very simple. All we have to do is first change the percent abundance into a decimal. So say in this case, I have a percent abundance of 99.98%. Okay, all we have to do is we have to change that to a decimal. We just divide by 100, or you can just move the decimal place over to the left 2 times. And that's where we get this number 0.9998. That is the decimal form of our abundance. And what we'll see is in hydrogen 2, we see that our decimal form is 0.000115. And then even smaller below it for hydrogen 3. And they're all in decimal form. The next thing we do is we multiply the atomic mass by the abundance in the decimal form. So basically all we would do is we'd take these 2 numbers and multiply them. Take these 2 numbers, multiply them. Take these 2 numbers and multiply them. And then lastly, we would add the contributions of each isotope. So we would get the sum of all of these, okay? We get, after we multiply them, we get our sum, and then all we do is we just add them all up, and we get the overall. And this number down here, that is actually our average atomic mass. That's what we see on the periodic table. Now, example B1, it says a particular mass spectrometer ionizes a sample to a stable form and then separates the components with different mass to charge ratios. Would a mass spectrometer be able of separating substances shown below? And we see we have calcium and we have sodium. We have calcium 40 and sodium 20. The one thing that we have to look at, is kind of a two-part question of what we're really looking at, is that it separates the components with different mass to charge ratio. So we're looking at our mass to charge ratio, so mass to our charge, so mass divided by our charge. And we have to see that it's ionizes. Well, the stable form of calcium is calcium 2 plus. Calcium stable once it loses 2 of its electrons, so it becomes more positive, has more protons, so it's 2 plus. Sodium, on the other hand, is stable with just one single electron loss. So it's going to be a cation, and it's going to have a 1 plus, since there's not a 1 there, just assume that it's there, a 1 plus charge. So if we're looking at mass to charge ratio, our mass is 40, our charge is 2 plus, so we get a mass to charge ratio for calcium of 20. And here we have 20 compared to 1, so our mass charge ratio is going to be 20 as well. So when we look at these two things, they both have a mass charge ratio of 20, so the mass spectrometer would not be able to separate those two substances out. Okay, example B2, it says, using the data below, determine the average atomic mass for iron. Main thing that we want to do here is we want to follow our rules. Remember, the first rule is change our percent abundance and put it in decimal form. So we're going to divide by 100, or move the decimal place to the left 2 times. So 1, 2, 0.0. Make sure you do that for every single one. The next thing, remember, we have to multiply the atomic mass by the percent abundance. Remember, when we're finished and we get all of those, make sure you add them up to get your average atomic mass. All right, example B2, another one. It says the average atomic mass of chlorine is determined to be 35.45. When accounting for the 2 naturally occurring isotopes, the 2 naturally occurring isotopes are shown below. We see we have our chlorine 35 and our chlorine 37. And we see that we have our atomic masses right there. What is the percent abundance of each isotope of chlorine? So basically we're working backwards. We have our average atomic mass and we want to work backwards to our percent abundance. The one thing I'll help you out here on, remember that all percent abundances, once they are in decimal form, they all equal 1. So if I don't know the percent abundance of chlorine 35, I'll just say that it's X. And then since I know that all percent abundances add up to 1, that means that chlorine 37's abundance should be 1 minus X. Okay? Make sure you can plug this into an equation and figure out your answer. You should have carbon, 6, and then 1, 4. You have to be able to tell me why that is the correct answer.